So in the last video we found out this solution, which is the solution due to an delta input at t equal to t naught, and this solution is the key for us to find our explicit expression for the Green's function. Now unfortunately this is not exactly the Green's function, but we are very close. So what we'll need to do is to use this to write a solution to some arbitrary input, and from that figure we finally will be able to determine the exact form of the Green's function. But at this point what we're looking at is almost exactly what we're looking for, almost, but not exactly. So let's see what polishing we'll need to do, but before that let us first understand, or at least develop an intuitive understanding for this solution through a figure. So this is the figure that I want you to look at. In this figure, of course, in the x-axis we have plotted t, and the y-axis we are plotting the functional value. And in this case, if you compare it with the equation above, considering that we are starting from 0, you'll notice that t naught is 0, of course. Then we have beta equals 1, which is very interesting. So that means beta is in a sense strong. Typically the values we plot under dampings for the beta values, we try some kind of fraction, 0.1, 0.2, try to keep it minimalistic, but still there is a lot of decay. But this time beta is 1, so that's a lot. Then the area, remember b was the area, so that is 10, and you notice in front of the exponential decay, by in front I mean to the left, you can see beta b is divided by omega 1. So b is the area, omega 1 is the frequency, like angular frequency like quantity. So in this case omega 1 equals 10, which is confirmed by this factor of 10 here. And this is the typical response to the delta input. Now in order to construct the exact form of the Green's function, let us now look at another figure, and this is a figure that we should be looking at very carefully, because this basically represents how a delta function can construct, or can be used to construct, any desirable function you like, assuming of course the assumptions of continuity and differentiability, etc. So you have this delta function, which is a distribution which has this 2 points of argument and a plethora of properties that it needs to satisfy. But in a sense, not only not it is a proper function, but also it's a limiting case of a series of functions. So what we are going to do is to see that before taking the limit with the tools we have just developed, that is the tool of impulse function, we can almost, with certain errors, so for example these areas are of course the errors, but nonetheless I think you get the idea how we can use the impulse function to recreate, or rather approximate, a given function, in this case f of t divided by m, so that's the exact function, and we want to recreate it, and we have used the impulse function. I'm assuming that all the impulse function have the same duration, which should be denoted by tau. So I should just go on by saying the duration of each impulse is tau. So this can be written as, in terms of the figure, t of n plus 1 minus t of n. So that looks like a recursive relation. So t of n plus 1 equals t of n plus tau. And we're already assuming the tau to be small, because at the end of it, we have to take tau tends to 0 anyway. So we can say from the figure we can essentially see how to recreate or approximate any force input by means of impulse functions. And there you go. We can further expand by saying keeping tau small, and even though we haven't specified how small we want tau to be, right now we can just impose the condition that tau is much smaller than twice pi over omega 1. So that's the scale that can be built from the system for the sake of comparison. Now, using that, we can write our differential equation as x double dot plus twice beta x dot plus omega naught squared x. And remember, on the right hand side, instead of any arbitrary function, I'm writing its approximate. So basically you have a bunch of impulse function over m, and you have to add them up, and there has to be presumably infinite of them. And even if there are not infinitely many impulse functions, you will be needing infinitely many of the delta functions. So the limits of the sum, yes, you can take it as finite, but it doesn't really matter, and you can write it as the sum over an, which is a function of the interval. So let's write it as a function of one of the n's of the interval, and you still have n equals negative infinity to infinity of an times I. So it's an impulse function, and as usual it should have 3 arguments, so t, tn, and t of n plus 1. So if we have to write the solution for individual impulse, for example like the nth impulse, the solution becomes an, which depends on t of n times tau. Remember, a times tau was b divided by omega 1, then e to the negative b, t minus t naught. Then we have theta of t comma tn plus tau. Then we have sine of omega 1 times t minus t naught. Well, in this case tn. Let's close the bracket. So that is the solution for the nth impulse, and in order to find out the solution at any time due to all the impulses, let me write that with some other color. All you'll have to do is to take over a sum. So put on a sum and take it over all of these solutions. So you have sum from n negative infinity to some capital N. Then you have this exact quantity. Well, I can just copy it, right? So let me just borrow this expression I've just written from here to here. I can also change the color like that. And right now it is a proper time to take the limit t tends to 0. Now in that limit, tn becomes the dummy variable over which we'll carry out the integration. Remember, this summation, which is applicable for discrete objects only, turns to integration sign when in the limit the summation as a discrete sum turns to the continuous sum, which is the integration. So that's that. The length over which each interval is defined turns to dt prime, and of course the sum of tau then f of n, it turns to integral over dt prime f of t and t prime. So in the limit, our solution turns to an integral from negative infinity to some t, a of t prime over omega 1 e to the negative beta t minus t naught. Well, in this case it's going to be t prime. Then there is a step function t comma t prime, and then we have sine of omega 1 t minus t prime, and of course instead of tau we have dt prime. Okay, so you compare between the two expressions. One is the discrete expression written in blue, and the other is the continuous expression written in black. Compare between the two, and I think it is very straightforward how to get to the continuous form from the discrete form. So now, if you remember, so recall f of t prime, which is the force, this is equal to m times a of t prime, and a of t prime, which is, by the way, the same a we have written here. So this a is basically the acceleration. If you're a bit confused about it, go back to the original differential equation. So let me try to remind you. So x double dot plus 2 beta x dot plus omega naught squared of x, this was equal to a times theta, or a times the impulse function. And remember that the unit is carried by a. So if you look at the left, this quantity, all of the terms on the left hand side are basically on the same footing as acceleration in the physical sense, right? Because x double dot is acceleration, so the units in the sum has to match. So all the terms must have the same units, and if the left hand side of an equation has the unit of the acceleration, the right hand side must, and the impulse function doesn't have any unit, so a must be the acceleration. So a is f divided by m, and we can substitute this in here, okay, and we find out the solution in terms of the external input function or external source or the non-homogeneous part. So substituting, we get x of t equals from negative infinity to t. So all the history up to this point will contribute to the solution that we see at the present moment. So we have f of t prime divided by m. Well, there was an omega 1, and then e to the negative beta t minus t prime, theta, which is a step function, t prime sine of omega 1, and then t minus t prime dt prime. Now we recall the definition of Green's function. So we have x of t equals from negative infinity to t f of t prime, where f is the source, then the Green's function, which is t comma t prime dt prime. So if we compare, then we finally find the explicit expression for the Green's function, which is t comma t prime. We could have also written t minus t prime. That would be fine as well, but this is e to the negative beta t minus t prime divided by m omega 1. Then we have theta, which is the step function with argument t and t prime, then sine of omega 1 t minus t prime. And that, I think I should box it up, that is the Green's function we were looking for. One of the things you'd notice that due to the construction, the initial conditions are built into the solution, so we don't have to think about the initial conditions anymore. And once you know about the Green's function, we can safely assume that you have figured out the complete solution and we have achieved our goal. I think it's a good place to seal the deal and to conclude that this is the Green's function, which is the response to a delta input, and using this we can now construct the solution for any external source or external input function. There are other ways to find out the same conclusion, and that's what we'll be seeing next. However, I believe since we have done this step by step, I've broken down all the steps, this would be the most intuitive way to construct the Green's function, which brings us insights not only for this problem but for any problem really. It is very intuitive, or at least it should be very clear what is a Green's function and exactly how do we construct it, even though this method of construction is not going to be present almost anywhere, because as you can see the length is huge, the steps are important but big, and frankly speaking there are many efficient ways, some of which we'll see in the next few videos. Bye for now.